In the previous class, we just saw the D'Alembert's principle, its a definition and the free body diagram. With the figure, we have studied the D'Alembert's principle. Now, we'll go for the derivation of the D'Alembert's principle. See, as you have seen in the figure, okay, there are four figures A, B, C, D and E. Okay, with respect to the figure, we will write the forces acting on the mass. The forces acting on the mass are the weight that is acting in the downward direction. The weight that is equals to what? M into G. So I have written downward. So in order to consider the sign while writing the equation. So the weight which is acting in the downward direction is given as mass into gravity, that is M into G. The other force acting is the spring force. In which direction the spring force is acting? The spring force is acting in the upward direction. It is restricting the moment of the mass in the downward direction. So it is acting in the upward direction. So therefore spring force is equals to K into, what is that? The displacement is delta plus X. K into delta plus X in the upward direction. The third force is the inertia force. The inertia force is what? M into X double dot. M into X double dot. The body moves in the downward direction. So therefore, the inertia force will be acting opposite to the direction of the motion, which is equals to what? Mx double dot. That is in the upward direction. So these are the forces acting on the mass. Now, according to D'Alembert's principle, we will write these forces in the form of equation. So what does D'Alembert's principle says? So according to D'Alembert's principle, the summation of inertia forces plus the external forces is equals to 0. Is equals to 0. So here we will substitute the forces. So the inertia force, okay, the forces acting externally, that is a spring force and inertia force. So inertia force is what? Minus mgx. So I have taken the sign convention as, for downward direction I have taken it as minus, and for the upward direction I have taken it as plus. So therefore mg, so it is minus mg because it is downward, and spring force and inertia force are k into delta plus x. It is upward, so therefore I have taken it as positive, plus inertia force, that is mx double dot. So plus mx double dot is equals to 0. Fine. Substituting the forces acting in the D'Alembert's principle, we get this equation. Now, I will open this bracket delta plus x, so that I will simplify and write it as minus mgx plus k into delta plus k into x plus mx double dot is equals to 0. See, we know that mg is what? The weight of the mass acting in the downward direction. It is equals to k delta. The second free body diagram, you can observe that there is the spring force which is acting in the upward direction, that is equals to k delta. So therefore, here in this equation, mg and k delta, they get cancelled. Why? Because mg is equals to k delta. So minus mgx plus mgx it becomes. So therefore it gets cancelled. And we are left over with mx double dot plus kx equals to 0. Fine. Now, this equation, I will write this equation such a way that I will divide this equation by m. So I get as x double dot plus k by m into x equals to 0. Now let me call this as equation number 1. Call this as equation number 1. We'll keep it aside there. And coming to our previous discussions, we know that the equation for simple harmonic motion is what? X double dot plus omega n square x into x is equals to 0. This is our standard equation. Let me call that as equation number 2. If you compare equation 1 and 2, What do you get? From equation 1 and 2, we observe that omega n square is equals to k by m. So omega n square is equals to k by m. Fine. So using this, you can find out the angular frequency. That is, angular frequency is what? Omega n is equal to under the root k by m. Its unit is radians per second. Radians per second. Similarly, we can find out the natural frequency. That is what? F is equals to omega n by 2 pi. The formula for natural frequency is given as F is equals to omega n divided by 2 pi. We already know what is the value of omega n. So therefore, 1 by 2 pi into square root of k by m. Since we know this equation that mg is equals to k delta, from this equation we can write that k by m is equals to what? G by delta. So therefore, this equation can also be written in the form of what? F is equals to 1 divided by 2 pi square root of G by delta. Unit of frequency is hertz or cycles per second. Fine. Now, time period. The equation for time period can be calculated if we know the frequency. Fine. So time period is what? Tp, which is equals to 1 by F. 1 by F. We already know what is F. So therefore, it is what? Reciprocal of the natural frequency. So reciprocal of natural frequency is what? 2 pi square root of m by k. So unit of time period is seconds. Fine. So this is the derivation of D'Alembert's principle. So the D'Alembert's principle is analyzed by considering the forces acting on the mass and consider the sign also. Substitute it in the form of equation according to D'Alembert's principle and then obtain the equations for angular frequency, natural frequency and time period. Fine. So we'll continue now again with the energy method. Now we shall discuss about energy method. The second one is energy method. The definition for this energy method is, it is based on the law of conservation of energy. What is that? Law of conservation of energy. What does law of conservation of energy says? The law of conservation of energy says that energy can neither be created nor be destroyed. Fine. But it can be converted from one form to another form. Energy can neither be created nor be destroyed. But it can be converted from one form to another. This is a statement of law of conservation of energy. Now we will apply this equation for our spring mass system. So let us consider an example. So this is a standard example where we have a spring and a mass. Let the mass be m and let the spring be k. This is the static position of the spring mass system. Now, once the mass is given certain displacement, it takes a new position. Okay, let me consider that this is the mean position and let me write that this is mean position. Fine. When the mass is given a displacement, let the displacement be taken as x. Let me call it as x. The displacement of the mass from the mean position is x. Fine. So what happens when the mass is pulled down? When the mass is pulled down to its extreme position, then the kinetic energy will be 0. The kinetic energy will be 0. What about potential energy? Potential energy will be maximum. Kinetic energy is equals to 0 and potential energy is maximum when it is under downward position, when you are pulling it. Right? Fine. What happens when you leave it? When you leave the mass? The mass moves upward. So at that time what happens? The kinetic energy will be maximum and potential energy will be equals to 0. So the mass moves up and down. So what happens? This change in kinetic energy from 0 to maximum takes place and the potential energy from maximum to 0 will be taking place. So kinetic energy and potential energy will be changing as the mass will be moving up and down. Here there is no damper to resist the motion. Since it is a topic that is we are going to discuss under undamped free vibration, so there is no damper to restrict the motion. So therefore the mass keeps on moving up and down. So that's why there will be a change in the kinetic energy and potential energy as the mass moves up and when it is down. So this is when it is moving down and this is when it is moving up. Fine. Now there are two forms of energy acting on the body. So there are two forms of energy acting on the body. What are those? One is kinetic energy, the other one is the potential energy. How many types of energies are acting? There are two energies. One is kinetic energy and another one is the potential energy acting on the body. What is kinetic energy? Kinetic energy is nothing but it is because of the motion. Motion of the body, motion of the mass. Whereas potential energy is because of two things. Fine? We'll write down that now. So let me write that. So there are two forms of energy. Two forms of energy acting on the body. Let me write down. What are those? One is kinetic energy. Kinetic energy is what? It is because of the motion. So kinetic energy due to motion. The other one is potential energy. This potential energy is because of two things. So they are, one is because of gravitational potential energy. Gravitational potential energy. And the another potential energy is due to strain energy. Strain energy because of the spring. So therefore strain energy due to spring. Due to spring. Potential energy is because of the gravitational potential energy as well as strain energy of the spring. And kinetic energy is because of the motion of the mass. Fine. So these are the two forms of energy acting on the body. Now we will use these two energy and write it according to the law of conservation of energy. Fine. Continuing with this one. According to law of conservation of energy, according to law of conservation of energy, what the law of conservation of energy says that the energy can neither be created nor be destroyed, but it can be converted from one form to another form. So that is what the total energy is equals to constant. We can write it as total energy is equals to constant. Fine. What is the total energy then? Total energy acting on this system. That is, it is the summation of kinetic energy and potential energy. So therefore, kinetic energy plus potential energy is equals to constant. Fine. Call this as equation number 1. Call it as equation number 1. Now, we want to substitute the values of kinetic energy and potential energy. So, for that, we will take a figure. Just fine. Now, write down. We know that. What is that? Kinetic energy is equals to half mv square. You know this equation? Half mv square. Instead of this kinetic energy is half mv square. What is v here? It is 1 by 2 m. As I said, if x is the displacement and x dot will be the velocity and x double dot will be the acceleration. So therefore, v square is nothing but what? X dot square. X dot square. So you know now kinetic energy is equals to what? Half m x dot square. Consider the figure for spring force versus deflection, where spring force is along y-axis and deflection is along x-axis. Deflection is along x-axis. Now, if you consider the spring force, okay, as you apply more force on the spring, just to pull down, what happens? The deflection in the spring will be more. So therefore, spring force, if it is more, deflection is also more. So if you plot a graph for spring force versus deflection, the nature of graph will be a linear one. It will be a linear one. Now, I'll just take down the area below the curve, that is the area below this, the hatched portion that I will consider. Now tell me, this distance is what? This is the spring force, that is F. Spring force is F. What it is equals to? Spring force is equals to what? K stiffness into deflection. Spring force is equals to K into X. Fine. Okay. This distance from here to here is nothing but what? The spring force F is equals to K into X. Fine. I have taken a hatched portion. I have considered this hatched portion below the curve. The area below the curve is what? It is a triangle. It is a triangle. Then what is the area of a triangle? It is half into base into height. Using that concept, we will solve the derivation of energy method. We will solve the derivation of energy method. So deflection, as you know, it is always X and spring force is F. Fine. Now, why we have taken this figure for spring force versus deflection? It is in order to analyze the potential energy. As we know, we have the equation for kinetic energy. We want to derive the equation for potential energy. So therefore, we have considered this spring force versus deflection. Fine. Now, potential energy is equals to, potential energy is because of what? The spring. So therefore, I have taken this spring force versus deflection. Potential energy is equals to area under the spring force is equals to area under spring force. Spring force deflection graph. What is that? Potential energy is because of the spring, which is nothing but the area under the spring force deflection graph. What is this hatched portion? It is nothing but, it is in the form of a triangle. So which is nothing but a triangular area. It is a triangular area. So means what? The area of this triangle is what? A is equals to what? Half into base into height. You know this. Half into base into height. So therefore, you know this equation. Area is equal to half into base into height. So using that, I will write my potential energy as potential energy is equals to half into, what is the base? Base of the triangle is what? X base into height. The height is what? K into X. So therefore, K into X. It is K into X. Fine. What it becomes then? Multiply X into X. Half K X square. Half K X square. Okay. Now you have got the equation for potential energy as well as kinetic energy. So therefore you can substitute in equation 1. So we have half m x dot square plus potential energy half k x square is equal to what? Constant. It is constant. Okay. Let me call this as equation number 2. Call it as equation number 2. Keeping this aside, similar to our derivation in our D'Alembert's principle, fine, we will take the simple harmonic motion equation. We know that the simple harmonic motion is given by x double dot plus omega n square x is equal to 0. Call this as equation number 3. Call it as equation number 3. Now we need to compare equation 2 with the equation of simple harmonic motion equation, and then we have to find out the value of x double dot. Fine. But when you observe in this equation, you do not have any term like x double dot. So therefore you need to differentiate our equation number 2. Now differentiating equation 2, differentiating equation 2. If you differentiate equation number 2, what do you get? That is d by dt of 1 by 2 m x dot square plus half kx square is equals to 0. Differentiating equation 2 with respect to t. Okay. Now, we'll differentiate. You get 1 by 2 m. 1 by 2 m. Differentiation of x dot square is what? 2 x dot. Differentiation of x dot is x double dot. 1 by 2 m. Okay. 2x dot x double dot plus 1 by 2 k. Differentiation of x square is 2x. X dot is equal to 0. Now, in this equation, 2 cancels. Here also 2 cancels. Fine. And you can see that x dot is common in both the terms. Fine. Taking x dot common, the remaining terms I will write inside the bracket. So I am left with what? Mx double dot plus kx is equal to 0. It is as good as writing this equation as, that is, mx double dot plus kx is equal to 0. So this is into multiply. So I bring this side, so that also becomes 0. 0 divided by x dot. This can be written as x double dot plus k by m into x equal to 0. Now you have your equation number 2 in this form. Now you can compare this with your standard simple harmonic motion equation. So when you compare this equation with this one. So let me call this as equation number 4. Call it as equation number 4. Comparing equation 4 with equation 3. What do you get? We see that omega n square is equals to k by m. Omega n square is equal to k by m. What is omega n? It is angular frequency. Angular frequency. Omega n is equal to what then? Under the root k by m. Unit radians per second. Using angular frequency, we can find out the natural frequency and time period. Therefore, natural frequency F is equal to omega n by 2 pi, which is nothing but, what is that? 1 by 2 pi. Omega n is what? Square root of k by m. Unit of frequency is hertz. It is hertz. Next, time period. Time period, that is Tp. Time period, which is equals to what? 1 by a reciprocal of frequency, which is nothing but 2 pi under the root m by k. Under the root m by k seconds. This is about the derivation of energy method. Right? In energy method, according to law of conservation of energy, you analyze the energies acting, substitute in the equations, find out the equations for kinetic energy and potential energy, then derive that equation, differentiate it, compare it with standard equation of simple harmonic motion and obtain the equations for angular frequency, natural frequency and time period. So what you observe in these 3 equations, they are similar to the equations obtained in the D'Alembert's principle. Fine. The third method is Rallies method. We shall discuss that now. R-A-Y-L-E-I-G-H. Okay. S. Rallies method. This is another method which is the extension of energy method that we discussed now. Fine. It is an extension of energy method. It is based on what? The law of conservation of energy. What does the law of conservation of energy says? That the total energy of a vibrating system is equal to maximum potential energy. That's what I said. When is potential energy maximum and when kinetic energy is maximum? That is, it is only when the body is under vibration. So, which we call it as total energy. So, the total energy of a vibrating system is equal to maximum potential energy. Fine? Okay. So, that is what? Total energy of a vibrating system is equal to maximum potential energy. As we saw in the spring mass system of energy method, that certain case potential energy is maximum and certain case kinetic energy is maximum. So therefore total energy can be either maximum potential energy or maximum kinetic energy. At any moment total energy is either kinetic energy or potential energy, or it may be a summation of both or sum of both. Fine. Considering the spring mass system, the Rallies method is extension of the energy method, wherein the total energy of a vibrating system is equals to maximum potential energy, and this total energy is either kinetic energy or potential energy, or it may be the sum of both. Now let us say, fine, considering now total energy is kinetic energy. Let us consider one energy at a time. So we will consider now total energy is kinetic energy. Then it can be expressed as if we want to express total energy in terms of kinetic energy, then I can write it as kinetic energy maximum is equal to, what is kinetic energy? Half mv square, that is x dot square. Okay. Now, if I consider total energy is potential energy, then potential energy maximum is equal to half k x square. Kinetic energy maximum, potential energy maximum. Fine. This is when total energy is equals to potential energy, and this is total energy is equal to kinetic energy. Now, leave it aside. I will take you to certain informations regarding the simple harmonic motion. We know that the simple harmonic equation is what? X equals to A sine omega t. This we have discussed in the definitions while discussing the definitions. Now, if I want x dot, what should I do? I should differentiate this equation. So, x dot is equal to fine, A, okay, differentiation of sine is cos omega t, and omega t is omega. So, this can be written as A omega cos omega t. Now, when velocity is maximum, that is x dot is maximum. When velocity is maximum, then cos omega t is very small. When x dot is equal to maximum, cos omega t is very small. So therefore we will neglect it. So what do you get? X dot is equals to a omega. Neglecting cos omega t. Fine. And what is maximum amplitude? Maximum amplitude is x is equal to a. That is the maximum amplitude. Using these two equations, in these equations, now the equation gets modified as half into m x dot square, that is x dot is equal to what? A into omega. So that is, I will write it as omega into a square. And what is x? X is equals to a. So therefore 1 by 2 ka square. We have the equations for kinetic energy and potential energy in terms of amplitudes. Fine. Okay. Now coming to the definition of Rallies method. What it says that the total energy of a vibrating system is equals to maximum potential energy, and it can be either kinetic energy or potential energy. So therefore we can write now as it can be either kinetic energy or potential energy. So therefore I can write it as, what is it? Potential energy maximum is equals to kinetic energy, or kinetic energy maximum is equals to potential energy maximum. So therefore, what is kinetic energy maximum? It is 1 by 2 m omega a whole square. Potential energy maximum is 1 by 2 ka square. Okay. Here, these two terms cancels. Okay. And a square also cancels. So therefore, we have omega a m omega a omega square a square is equals to k a square. I am just splitting it and writing. A square also cancels. So therefore we are left with m omega square is equals to k, or omega square is equals to k by m, or omega is equals to root of k by m, which implies it is nothing but omega n is equals to under the root k by m. It is radians per second. It is radians per second. What is omega n then? Omega n is your angular frequency. Angular frequency is under the root k by m radians per second. As in our previous derivations, we will find out now natural frequency of at time period. What is natural frequency then? Natural frequency is what? F, which is equals to natural frequency. F is equals to omega n by 2 pi, which is 1 by 2 pi. What is omega n? It is under the root k by m. And frequency is always expressed as hertz. Frequency is always expressed as hertz. Time period Tp is equals to what? Reciprocal of natural frequency, that is 1 by f. So it is 2m 2 pi square root of m by k. Unit is second. So again you can observe that the equation for angular frequency, natural frequency and time period are similar to the energy method or D'Alembert's method. Fine. So D'Alembert's method is also called as equilibrium method, energy method and Rallies method. So with this, okay, we come to know that the derivation for all these three are same in all the three methods. Fine.